we are taking up a new chapter today, that is regarding nuclei, the part of nuclear physics what we are dealing with. In fact, all of you know well, even from this chapter also, in recent years, they are asking few questions at JEE level. And one should understand, first of all, before taking up this topic, what are the concepts we are going to deal with in this particular chapter. All of us, we know well the general construction of an atom, about nucleus, the properties of nucleus, and some of the important features related to nucleus, such as radioactivity. That's one part what we people are going to deal with in this particular chapter. In addition to that, about nuclear fission, nuclear reactor, the types of nuclear reactors in that, then about nuclear fusion and what exactly the source of energy in the case of the sun and in the case of the stars. About that one. In addition to these concepts, we are dealing with a small part of elementary particles. What is the general classification and what are the examples for each kind of the classification like. And in addition to that, we are going to discuss about quarks. So this in brief, we are having in this particular chapter of nuclei, which of course deals with nuclear physics as such. One of the easiest chapters we are having, and of course mathematical oriented, particularly while discussing about the problems on binding energy, mass defect. One need to have complete command over mathematics, basic mathematics only, just multiplication, that addition, subtraction, like that. So these areas we are going to deal with in this particular chapter, nuclear physics. Let me start with few applications based on radioactivity first. While discussing about radioactivity, one need to understand few basic concepts. They are the theoretical things I am talking about. The spontaneous generation of radiation in the form of alpha, beta or gamma, that's what is called radioactivity. When we discuss about radioactivity, alpha particle suppose is emitted by a nucleus. One should immediately get to your mind, rather, the mass will be reduced by 4 units and the charge will be reduced by 2 units. In the same manner, when a beta particle is emitted by a nucleus, mass will not have any variation, whereas atomic number that will be increased by 1 unit. For example, if gamma particle is being emitted, then neither mass changes nor the charge that changes. That means atomic number also is not going to be varied. So these areas commonly one should understand. In addition, what is actually alpha particle? Alpha particle is helium nucleus what we used to take up. And what about beta particle? A fast moving electron, almost negligible mass. We all know well, electron mass is 9.1 into 10 power minus 31 kg, which of course among all the elementary particles, electron is going to have the least mass almost. So almost every other elementary particle's mass will be given in terms of electron mass only so many times like. So that is one more concept you need to understand. So these areas we have to go for. And of course, the very first problem, let us take now some problems, some applications based on radioactivity first. Let me just read out the very first problem and let us discuss all those things in a detailed manner. First problem says, if N naught is the original mass of a substance of half-life period 5 years, then the amount of substance left after 15 years is how much? Half-life of that radioactive substance is 5 years, yes, given. After 15 years he is asking, that means 3 half-lives are over. 1. And what are the options given? It is the first option n0 by 8. The second option is n0 by 16. Third option is n0 by 2. And fourth option is n0 by 4. This question has been given in 2007 in AIEEE paper. So one should understand the way they are just dealing with the questions at the final examination level. So this type of a question anytime we can expect. So let us remember what exactly the formula that is to be taken up for this. Let me remind you a few cases first. So let me remind you first of all few concepts of this radioactivity. When you talk about radioactivity, N is equal to N0 e power minus lambda T. This is radioactive disintegration law. All of you know pretty well here, N0 is the number of elements present in the radioactive substance when time taken is 0, and N is the number of radioactive elements left in that substance after a time, say T. And what is this lambda that is called? Lambda is called disintegration constant or decay constant, we can call it. And what is the formula for this lambda? Lambda is equal to 0.693. That is, we used to take half-life period is equal to 0.693 by lambda. This of course you can write even lambda is equal to 0.693 by T. This is the second formula you need to remember. Coming to the next one, 1 over lambda, that's what we used to call it as average life. This is another point what we people have to remember. Therefore, what is the relation between half-life period and average life? Half-life period is equal to 0.693 times average life. That's what actually we can write from this equation. Exactly in the same manner, a very commonly used formula is N by N0 is equal to 1 by 2 whole power T by T. You can straight away understand this formula. N is the number of elements present after time T. N0 is the initial number of elements when time taken is 0. And what is this small t here? Small t is the total time and capital T gives you half-life period. So you can even rewrite the same equation this way also, 1 by 2 to the power n. What is that n that is giving us? It is a number of half-lives which have been taken place. So if you can remember these equations, almost 90% problems you can solve. The remaining 10% means their applications. Directly we can take up that equation then and there itself and tackle the problem over there. That is the general methodology. So if you look at this particular question, that's problem number 1. N0 is the original mass of a substance of half-life period 5 years. So we can all understand well, when half-life is given 5 years and the total time after which he is asking you the remaining, that is 15 years, what can we understand from this lot? Number of half-lives taken place is going to be simply 3. So identify that concept first of all. Then what is it he is asking? The amount of substance which is left. And one should be very, very careful in reading the question. Whether he is asking you the amount of substance left over there or the amount of substance which has been decayed over there. It is now left amount he is asking. Therefore, you directly can go ahead with that formula. N by N0 is equal to 1 by 2 whole cube, because 3 represents the value of n over there. So directly 1 by 2 whole cube, which now becomes 1 over 8. Then how much is remaining is the question. N now becomes n naught by 8. So how much that is remaining over there? 1/8 of the total amount of substance that is undecayed. Suppose if that fellow asks you, what is the amount of substance that has been decayed already in this time period of 15 years, then you should understand when 1/8 is remaining, it is understood 7/8 has lost. Has been lost in the sense what? Has been decayed. That is the concept what you have to understand. So if you look at this value and tally with the options given over there, very first option is given n naught by 8. Second option n naught by 16. Third n naught by 2 and fourth n naught by 4. So exactly this value is in coincidence with the very first option what has been given in the problem. So we can directly say the answer for this particular problem is A. That is the first problem what we have in this order, which has been asked way back in 2007 AIEEE paper. Remember this concept. Okay, so this is problem number 1. Let us take the next number here. That's problem number 2. When uranium-238 nucleus, originally at rest, decays by emitting an alpha particle having a speed u, the recoil speed of the residual nucleus is how much? This particular question is linked up with the concepts of dynamics. Particularly, it is based on the law of conservation of linear momentum. We all in fact know well the collisions between fundamental particles or the concept of radioactive decay. All these things they come under elastic collisions like. So considering the law of conservation of linear momentum over there, we can deal with this type of a problem. And what are the 4 options given? First option is 4u by 238 with positive sign, of course. Second option is given minus 4u by 234. And third option is given 4u by 234 with positive sign. And fourth option minus 4u by 238, that is with a negative sign he has given. So what is it he is giving? Once again let me give out. Uranium-238 nucleus is originally at rest. It is now decaying by emitting an alpha particle with a velocity say u. That's what has been mentioned. So first and foremost you can understand here, say this one is uranium-238. It is initially at rest. So you can understand its initial velocity, we can take it as 0. Now it is giving out an alpha particle. All of you are aware of alpha particle is nothing other than helium nucleus. So helium-24 we people used to represent this alpha particle. What is now remaining? You can certainly understand the other one. If I take it as x the element, then it will now have 234 as its mass number, and of course this is 92 generally. This will now be 90 as its atomic number. So you can certainly understand uranium-92-238. When it is decaying into alpha particle and another element of mass number 234, what is the speed of this one he is asking. So if I take the velocity of this one is given as u, what is the velocity of the second element? That is the question he is asking. So first and foremost, according to the concept of law of conservation of linear momentum, we now can write this step like this. mu is equal to m1v1 plus m2v2. That is the basic equation what all of us we know. This now can be rewritten as 0 is equal to the mass of helium, that is alpha particle, is 4 units. 4u plus here 238 minus 4, 234 into V2. So what is the velocity here? V2 is equal to now 4u by 234 with a negative sign, no doubt. That is the velocity. But carefully read the question. What is the question he is asking? The recoil speed of the residual nucleus. That recoil word itself means that it is moving in opposite direction. That means the very negative sign is very much there in the same question itself, in the wording itself. So once again you need not put this negative sign before the value. Therefore, what we should understand here, recoil speed now is going to be simply 4u by 234. That is the concept you need to understand. So what is the correct option for us? Look at the third option, 4u by 234 he has given. Suppose if the question is what is the velocity of that body, that in the sense he is asking you recoil speed. Speed means we need not consider the direction. It is a scalar and its value is to be taken up there. So directly you can write 4u by 234. So you can say the correct answer over here is going to be simply C. That is the one what has been given there. Look at 4u by 234. That is going to be the recoil speed of the residual nucleus in this particular question. No doubt it is the concept of nuclear fission like idea is okay, but it is linked with the concepts of mechanics, particularly dynamics part. That is law of conservation of linear momentum has been linked up with this. This is the way we people just have to work out the problem for problem number 2. That is the case 2. Let us switch over to problem number 3 here. A radioactive sample at any instant has its disintegration rate 5000 dpm. That of course all of you can understand disintegrations per minute. After 5 minutes the rate is 1250 dpm. That means 5000 has now become 1/4. That is the understanding we need to have while reading the problem. Then the decay constant per minute is how much? Generally decay constant means number of disintegrations taking place or observed over there per second we write. But he has given every value in terms of minutes. So he is asking you even the answer also per minute only. So no need for us to convert any of the values given there. So what are the 4 options? First option is 0.4 log 2 to the base e. Second option is 0.2 log 2 to the base e. Third option is 0.1 log 2 to the base e. And fourth option is 0.3 log 2 to the base e. What is the correct option out of the 4? Now look at first of all what have been given. If I just take n as something like 5000, right, disintegrations per minute, that's what has been given there. Radioactive sample at any instant has disintegration rate that much. Now after 5 minutes he is just talking about 1250 dpm it has become. So now this is original. If I take this one 1250 dpm like, and of course he has given you after 5 minutes, that is the time that has been given. After 5 minutes, that is what actually he is giving you the time over there. And what he said, then the decay constant per minute, what is the value of lambda, that is the concept. Now you can all understand straight away. n is equal to n naught e power minus lambda t. Out of that, t is known to you. N and n naught directly we people can take up directly like that. And we just want the value of lambda, that is the calculation needed to be taken up. So you now can rewrite the same this way, n over n naught, that is 1250 by 5000. That now is going to be e to the power minus 5 lambda. Because t is given 5 minutes, I am directly taking that one as it is. So you can even rewrite the same as 1 by e power 5 lambda. So this anyhow goes 4 times, we know. Then what can we write now? E to the power 5 lambda 4. Directly we can write. You can equate the denominator values. This 4, you better take this one as 2 square like. Whatever we people are taking up this way, also you can better understand. In fact, log 2, he is giving the options in terms of log 2, not in terms of log 4. All the 4 options we are having log 2 like. So better write 2 square, this 4 value as. Now you can write this e to the power 5 lambda is equal to 2 square. Come on, take the logarithms, logarithmic values there. So what can we write now? This now can be rewritten this way, 2 log 2 to the base e. That now is going to be simply 5 lambda. So when you take logarithms on both sides, 2 log 2 to the base e, that now becomes 5 lambda for us. So what can we write now? Lambda is equal to 2 by 5, which is 0.4 log 2 to the base e. This must be the value of lambda, which is called the decay constant or disintegration constant. In this case, since time is given in minutes, it is per minute he is asking us. We also are going to get per minute value only. So what is the correct option that is given? See the very first option, 0.4 log 2 to the base e. Same value we have got here after calculation. So we can say the correct answer for this particular problem is A. So what you need to take up in this case? N is n naught into e power minus lambda t. Out of that, what are the values given here? They are proportional to this also. You can take n naught and n. Directly also you can take, or you can think of they are proportional like, no worry. So this is the equation ultimately you have to take up to deal with this problem, and lambda now becomes 0.4 log 2 to the base e. That is the correct option for us, and it is the first option which is given correct in the problem as such. Next problem is a wonderful model question here. It is based on the radius of the nucleus. Not in fact one, of course nuclei he is asking. Let me read out the question first. A nucleus disintegrates into 2 nuclear parts which have their velocities in the ratio 2:1. The ratio of their nuclear sizes will be how much? Nuclear size means it is the radius only. That's what generally we people used to take up. And all of you know very well, size of the nucleus is in the order of Fermi. 1 Fermi is going to be 10 power minus 15 meter. And of course, the size of an atom, when we consider, that is in the order of angstrom unit, like 10 power minus 10 meter. So these conversions and these values are known to us all. I'm simply reminding you, that's all. Now look at the options given for this problem. First option is 2 power 1 by 3 is to 1. And the second option is 1 is to 2 power 1 by 3. And the third option is 3 power 1 by 2 is to 1. And fourth option is 1 is to 3 power 1 by 2. So these are the 4 options mentioned. So let us start the problem this way. He is giving you velocities there. And one nucleus is disintegrating into 2 nuclear parts. That's what has been mentioned. So if I take the velocity ratio V1 is to V2 is given 2 is to 1. So in true sense, you can understand well, masses are in the inverse ratio of their velocities. What for also people can understand? When initially the original nucleus is at rest means its momentum will be 0. That now can be written as m1 v1 plus m2 v2 according to the law of conservation of linear momentum. Already we have taken up one application based on the same formula in the previous problem. So if you look at this, m1 v1 and m2 v2 are equal but opposite. That time, what would be the relation between velocities and their masses? You can say v1 by v2 must be equal to m2 by m1. But you need not take the direction here into consideration. I am just talking of their magnitudes. That is the concept. Direction, if you look at, one goes opposite in direction to that of the other. It is understood anyhow. We all know that point very well. Now if you look at this, when v1 is to v2 is 2 is to 1, I now can write m1 is to m2 as 1 is to 2. So you can all understand this way if I write m1 by m2 is equal to 1 over 2, but nucleus is supposed to have spherical shape. In fact, we theoretically say nucleus has no boundaries. But still, for all practical calculations and other things, like we people consider that the shape of the nucleus or shape of an atom as a whole, that is taken to be spherical by nature. So if such is the case, mass is directly proportional to r cube. That also one should get to your mind rather. What for? Mass is equal to volume into density. That is the general formula what we people used to take. For a spherical object, volume is 4 by 3 pi r cube. Density okay, rho. Then what can we understand now? Mass is directly proportional to r cube. So what I can write here now? This is equivalent to r1 cube by r2 cube. So what you can understand from this? r1 by r2 now becomes 1 by 2 power 1 by 3. So the ratio of radii I have just taken up. What for also you people can understand straight away. Now his concept is, what is the ratio of sizes of the nuclei? Nuclear size means it is in terms of radius only we people is to take up. So here the ratio of radii is the question. So what will be the value now? You can write r1 is to r2 as 1 is to 2 power 1 by 3. This must be the correct relation. So which option that is tallying with the 4 options given over there in the problem? Look at the second option. He says 1 is to 2 power 1 by 3. Therefore, the answer for this particular problem is going to be B. So 2 things we people have taken up in this problem. Let me be in brief. First and foremost concept is, whenever the disintegration takes place, that system obeys law of linear moments. That in the sense, law of conservation of linear momentum. That's the point. If you take up this one, m1 v1 plus m2 v2 is 0, velocities are inversely proportional to their masses. That is one area. And second thing what we have taken up is, since the shape of the nucleus is taken to be spherical by nature, we can consider that mass is directly proportional to R cube here. So taking that relation, we just have estimated the sizes of those two nuclei. In terms of their radii only, we people used to say that. So R1 is to R2 will now be 1 is to 2 power 1 by 3. That is the correct answer for it. That is the second option which is correct for this problem number 4. Take the next problem, that is problem number 5. Starting with a sample of pure copper 66, 7 by 8 of it decays into zinc in 15 minutes. The corresponding half-life is how much? This question has been given in 2005 in AIEEE paper again. So what are the 4 options mentioned? You see first. First option says 5 minutes. Second option is 15 minutes. Third option is 10 minutes. And fourth option is 7.5 minutes. That's 15 by 2 minutes he is talking about. So what he has given, once again you look at. Starting with a sample of pure copper 66. 7 by 8 of it decays into zinc. 7 by 8 has been decayed. Then what is remaining? What is the remaining amount? It should be 1/8. 7/8 has been decayed means 1/8 is left over. So how to write that concept now? N by N naught is equal to 1 by 2 to the power T by T. There is a formula like this which I have already reminded you before taking up this topic today. If you consider N by N naught is equal to 1 by 2 to the power T by T, small t gives you total time. Capital T gives you half-life time. If you look at N by N naught is now given 1 by 8. How do you know that? Look at once again the value given. 7/8 has been decayed. Very simply speaking, 1/8 is still remaining. That remaining amount only we want. So 1/8 is now going to be 1 by 2 to the power that T is given. How much he has given the total time? 15 minutes. So I write 15 minutes by capital T. But you all can understand 1 by 8, we can write that one as 1 by 2 whole cube. So what can I write from this one? 15 by T must now be equal to 3. What for you can better understand this 1 by 8? I can write that one as 1 by 2 whole cube. This 3 and this 15 by T being powers of the same quantity, you can directly equate them. Then what is left over here? T now becomes 15 by 3, which now becomes 5 minutes. This T itself is called half-life period or half-life time. If you take T 5 minutes, look at the options as I have already read earlier. First option is itself given as 5 minutes here. So the correct answer for this particular problem is going to be A. So once again, N by N naught is equal to 1 by 2 to the power small t by capital T. That is the equation. Out of that, small t gives you the total time and capital T represents half-life time of that radioactive substance what has been given there. So this is the methodology you have to adopt and this is the answer for it. The same question has been given in 2005 in AIEEE paper, I have already told you earlier. So this is problem number 5 for us. Check the problem number 6 now. If radius of aluminum 1327 nucleus is estimated to be 3.6 Fermi, then the radius of an element X having 52 as its atomic number and 125 as its mass number, that nucleus will be nearly how much? So he is just asking us what is the radius of that nucleus. And of course this question, once again I repeat, this has been given way back in 2007 JEE paper. The four options are given this way. The first option is 4 Fermi, the second option is 8 Fermi, third option is 6 Fermi, and fourth option is 5 Fermi. So these are the four options given. What is happening first of all here, you understand. Aluminium is now becoming into an element something like X he has given. Aluminium of course is going to have 13 as its atomic number and 27 as its mass number. What about of X he has given? Look at once again, it's given 52 as atomic number and 125 as mass number. So aluminium nucleus radius he has given. What is the radius of this one he is asking? Simple. It's not becoming that or something like. Radius of this one is given. What is the radius of that is the question. What is its radius that has been given here? 3.6 Fermi. What about its radius, the question? Come on, first of all recollect what is the formula for radius of the nucleus. If I write that one over here, R is equal to R naught into A power 1 by 3. All of you are familiar with this formula. R naught is constant of proportionality there, around 1.4 Fermi we people used to take that value. And A power 1 by 3, that A stands for atomic mass or mass number over there in that case. So if you take this equation, R is directly proportional to A power 1 by 3. That is the relation we people have to take up here. So what I can write now from that? R of aluminium by R of the element X, that is supposed to be equal to A of aluminium by A of this element X whole power 1 by 3. You can understand well the value of mass number here is 27 and here is 125. You can write 27, here 125 to the power 1 by 3, that is cube root. Cube root of 27 is 3 and 125 is 5. So what is the value he is asking? What is radius of that nucleus which has been given as X? So Rx now is going to be 5 by 3 times the value of radius of aluminium nucleus. What has been given of radius of aluminium, you all know that. So it is 5 by 3 times 3.6 Fermi. This of course goes 1.2 times. So it now must be 6 Fermi as such. So you should get 6 Fermi. That is the radius. But one should recollect once again this formula thoroughly. R is equal to R naught into A power 1 by 3. That is the general equation for calculating the radius of any nucleus. And all of you know pretty well radius is simply depending on the mass number there, nothing else. R naught anyhow is a constant. So we can directly write the same equation to solve this problem, and 6 Fermi the answer I have got, which of course is the third option given in this problem. Therefore we can write the answer for this problem is C. So remember that R is equal to R naught A power 1 by 3 formula, from which R can be directly proportional to cube root of A or A power 1 by 3. That is the one which you have to remember for this problem, and this has been given in 2007 JEE paper. Check the next number, that is problem number 7 for us. Two radioactive materials X1 and X2 contain same number of nuclei. That is the first statement given. The number of nuclei what x1 has got, the same number x2 also has got. If 6 lambda per second and 4 lambda per second are the decay constants of x1 and x2 respectively, the ratio of number of nuclei undecayed which are left, which are not decayed, that's what he is asking, of x1 and x2 will be 1 by E. After what time? He is just giving you the 4 options like this. 1 by 2 lambda seconds, second option 1 by 10 lambda seconds, and third option 1 by 5 lambda seconds, and fourth option 1 by lambda seconds. That's the question given. So first and foremost, he is just giving us x1 as the first element, x2 as the second element. For this particular element, what is lambda 1 given, you see? That is the decay constant he has given directly there. It is given 6 lambda for this. And the decay constant of the second element is given 4 lambda like this. So 6 lambda per second, 4 lambda per second. And of course, both he has mentioned in the problem have the same number of nuclei initially. That's what has been mentioned. Fine. Now the ratio of number of nuclei undecayed of x1 and x2, that ratio is supposed to be 1 by E. That is what has been mentioned. So what I can write for the first one, you look at first. I can write n is equal to, that is n1 I write, is equal to n naught into e power minus lambda 1 t, that is minus 6 lambda t. That is my first equation for the first element. What now I can write here? n2 is equal to n naught into e power minus 4 lambda into t. But observe carefully in both the equations, both n1 and n2 are the corresponding amounts which are undecayed of x1 and x2 respectively. That ratio he is asking. So what we should understand from this now? n1 by n2, which is equal to e power minus 6 lambda t by e power minus 4 lambda t. This ratio is given as 1 by E in the problem. So I think all of you might have understood this n1 by n2 ratio is given as 1 by E. After what time it becomes 1 by E, the question. So when I take the ratio here, can't you just simplify this one? Take this one up. It's now going to become e power minus 2 lambda t, that is 1 by E. You can even rewrite the same this way, 1 by e power 2 lambda t is equal to 1 by E. That implies 2 lambda t must be equal to 1. Then what will be the value of t? 1 by 2 lambda. So after what time the ratio becomes 1 by E? That is the question. 1 by 2 lambda, everything is giving per second like. So automatically this also will be in terms of seconds only. The time after which the value of n1 by n2 is going to become 1 by E. That is 1 by 2 lambda seconds for us. So this 1 by 2 lambda seconds, according to the 4 options given over there, it is the first option given there. So directly you can remember the answer for this particular problem as A. That is problem number 7 for us. Problem number 8 has been given way back in 2002 IIT paper. Let me read out the problem. The half-life of 80 to 15 is 100 microseconds. The time taken further radioactivity of a sample of 80-15 to decay to 1/16th of its initial value is. It should now become 1/16th. Simple concept here is like this: 15/16 part of that particular sample has been decayed. 1/16th is remaining. Means what? 15/16th part of that sample which has been taken up there has been decayed already. After what time this happens like this? That's what is the question. So first option is given 400 microseconds. Second option is given 6.3 microseconds. Third option 40 microsecond and fourth option 300 microsecond. If you look at the case, he is just giving you half-life of that element as 100 microseconds first. That's already given. Let the element be anything, that hardly matters for us. And we know 1/16th of the total amount is now left undecayed. So we can directly write this way: n by n naught now must be 1/16. This, of course, you can write the same like this: 1/2 to the power 4. But truly speaking, this has a formula. What is that? 1/2 to the power t by t is equal to n by n naught. That is the formula actually what we know. Now you can say this one and this one are going to be equal according to the values given. So what we can predict directly from this? T by t, that now must be 4. And all of you are familiar by this time. Small t refers to the total time after which it is becoming that much. And capital T is the half-life period of that particular element given. So we can now understand from this, T must be 4 times the half-life period. Half-life time is given as 100 microseconds. So it now should be 400 microseconds as such. 400 microseconds, according to the given options, it is the very first option that is tallied with this calculated value. So if you look at so far the questions what we have taken up, most of the questions can be worked out by taking this formula. N by n naught is equal to 1/2 whole power small t by capital T. If you can remember this formula thoroughly, almost 75 to 80% of problems you can clear off. The remaining problems, you may have to apply the case in a different way. That's all. Formula is same. N is n naught into e power minus lambda t, the basic equation. From that only we people are getting all these. So this is actually the question number 8 what we have. The correct option is 400 microseconds, which is the first option given in this problem as such. Check the next number, that is problem 9. Activity of a radioactive element decreased to 1/3 of its original activity I0 in 9 years. After further 9 years, its activity will be how much? I am repeating once again. Activity, initial value has been given I0 of a radioactive element. After 9 years, it has become 1/3 of the original value. After further 9 years, what would be its activity? That is the case. And of course, options are given this way. The first option as I0. Second option as 2I0 by 3. And third option is given as I0 by 9. And fourth option is given as I0 by 6. First and foremost, you should recollect what is meant by activity. Activity is lambda times n. In fact, lambda is called decay constant. N is the number of elements of that radioactive substance which has been undecayed at that time, or which are still remaining at that time. That n lambda, that is what is called activity. So if you start this equation like n is equal to n naught e power minus lambda t, that is a general equation, okay. You can now multiply this one both sides by lambda. This will be the present activity, this will be the earlier or original activity. That is what has been given. So after 9 years, activity has become 1/3. That is the concept what has been mentioned. So first of all, you can think of this now is going to be n by n naught, that is lambda n by lambda n naught, that is e power minus lambda t. This value is given as 1/3. The activity now is becoming 1/3. After how many years? After 9 years. That's what has been given. Therefore, you can rewrite the same this way. E power lambda t is equal to 3. In other words, you can even write the same this way. E power 9 lambda is equal to 3. So you can even understand this concept like this. Log 3 to the base e is equal to 9 lambda. Like that also you can remember. So n by n naught is going to be 1/3 after 9 years. That is the concept what he is talking. So this is actually the relation what we people can predict. Out of that you can even write the same this way. Log 3 to the base e will now be equal to 9 lambda. This also you can remember as the outcome of this calculation. Fine. Already it has become 1/3. Now the question is, after further 9 years. In fact, you people can identify here itself. After 9 years, activity has become 1/3. Further 9 years, activity becomes how many times? 1/3 square times. So how much it should now be? 1/9. That is the concept. So you can even remember that way. Otherwise, you can once again rewrite the equation and calculate the rest. What is the present value here to be taken? Lambda n by 3 to be taken here. And what is this value now? Lambda n by 3 means after further 9 years. After further 9 years. What would be the activity? Activity now becomes lambda n by 3 square. Here of course it is becoming lambda n by 3. Further 9 years into 1 lambda n by 3, 1/3. How much? So totally you can say I naught by 9 times it is going to be. Even you need not calculate this value also. By looking to the values you can predict. So activity after 9 years is becoming 1/3 means after further 9 years it becomes 1/3 of 1/3. It definitely becomes 1/9. So original activity has been given I naught. So it now becomes 1/9 of the total value. So what we can understand here, the correct answer that has been given according to the 4 options is tallied with C now. So you can directly say it is now becoming 1/9 of the original activity. 1/9 of original activity is given I naught. So straight away you can write that one as I naught over 9. That is the correct answer for us, which is the problem number 9 for us. Problem 10 has been given almost in every entrance examination so far. All over India I am talking about. A radioactive nucleus can decay in two different processes. It is decaying now in different processes, like he is giving two different processes. The average life for the first process is T1 and that for the second process is T2. The effective average life is how much? That is the question. I once again repeat, a radioactive nucleus can decay in two different processes. The average life for the first process is T1 and that for the second process is T2. The effective average life is how much? Four options are mentioned once again. The first option says it is under root T1 square plus T2 square. The second option says it's T1 T2 by T1 minus T2. Mod of that value has been given there because we do not know T1 is more or T2 is more. And the third option is T1 T2 divided by root of T1 square plus T2 square. And the fourth option is T1 T2 by T1 plus T2. What is the correct option for it? When he is talking about average life values are given, average life is known to us all as 1 by lambda. But we people can understand in this particular case, lambda must be equal to lambda 1 plus lambda 2. That is the total average or effective average life, like we just want. This now can be taken 1 by T is equal to 1 by T1 plus 1 by T2. What I can write from this one? T1 plus T2 by T1 T2. So what will now be the effective value of T? That's what he is asking you. So T must now be equal to T1 T2 by T1 plus T2. Just look at this option where it is going to be, it is given over there. It is the fourth option that has been given. Therefore, the answer for this particular problem is going to be D as such. That is question number 10 what we have. Problem 11 is purely a theoretical concept, like you people need to know the method of doing each and every calculation. Like for a certain radioactive substance, it is observed that after 4 hours, only 6.25% of the original sample is left undecayed. 6.25%, observe this wording carefully, this value. 6.25 by 100. Is it not 1/16th, please? So you can understand 1/16th is left undecayed. So what we can understand? 15 by 16th part of the total substance has already been decayed. So you can straight away understand 1/16th is left undecayed. That's what has been given. It follows that he has given us 4 options. We have to check each and every option to find out the correct answer for that. Because it is a multiple answer type of a question. So first option he said half-life of the sample is 1 hour. Let us work out each and every one there. First option is given half-life is given 1 hour. Now let us calculate this value. How? We know very well n by n naught, which is 1 by 2 to the power t by t, is now 1 by 16 according to the given value. 6.25%. 6.25 divided by 100, that now becomes 1/16th. So 1/16, can't you just write 1 by 2 whole power 4? Now come on, equate these two. What will you get? T by t is equal to 4. And what is half-life period? The question. Capital T is T by 4. T is given 4 hours. This also is 4. So what is the value now you are getting? 1 hour must be the half-life period of that element. So what is the first option given? You look at the half-life of the sample is 1 hour. Yes, it is 1 hour. So first option is correct. Let us check the second option, what has been given in this order. The mean life of the sample is 1 by log 2 to the base e hours. Mean life of the sample. Observe, average life he is talking about. We all know very well average life. Average life or mean life, that is 1 by lambda. In reality, we all know what is this formula for lambda. Lambda is 0.693 divided by the value of half-life. So what we can understand 1 by lambda in this particular case, you will be getting 1 by lambda, which now is going to be, in terms of lambda I am talking about, lambda is 0.693 by half-life. Now 1 by lambda he is talking about. So what is the corresponding value there? It is half-life period, that is 1 by, right, 0.693, which all of you are very much familiar. This is log 2 to the base e. 0.693 has got its own importance there. It is log 2 to the base e. That is what has been given in the second option. These many hours is the value of average life he has given. This is also true according to the given options. So I think all of you might have got this particular conversion or calculation. Lambda is 0.693 by t half. The t half now becomes this half-life 1 hour by 0.693. 0.693 is nothing other than log 2 to the base e. See the third option now. The decay constant of the sample is log 2 to the base e hours. Decay constant, that is per hour we should have. Decay constant means lambda we want. When 1 by lambda is this much, what will now be the decay constant? Observe carefully. Decay constant is lambda. Reciprocate this. It is to be log 2 to the base e per hour. So the same he also has mentioned in the third option. So decay constant of the sample is log 2 to the base e per hour. So even C also is correct. Now one more option is left over. Let us check even whether that is correct or wrong. After a further 4 hours, the amount of the substance left over would be only 0.39% of the original amount. First and foremost, observe carefully, after further 4 hours, already first 4 hours he has given, further 4 hours he is giving, so total is supposed to be 8 hours. And we know pretty well, 1 hour is its half lifespan. That means how many half-lives are taking place here? 8 half-lives are taking place here. So what is now remaining? He is asking you, come on, write down that value d over here. D is equal to n by n naught is 1 by 2 to the power 8. What for you people can directly understand? First 4 hours, next 4 hours, total 8 hours. And half-life span is 1 hour. That means 8 half-lives are taking place. So after 8 half-lives, what is now remaining? Just look at this equation. N is equal to n naught by 1 by 2 to the power 8. 1 by 2 to the power 4 is 16, okay. 2 to the 4, 4 to the 8, 8 to the 16, then 32, then 64, then 128, and the next one we people have to take up 256. So that is a value. So you can directly write 256. So probably you all might have got that. Right, 2 to the power 8 we people are having, 2 to the 4, then 8, then 16, then 32, then 64, then 128, then 256. What is this value? You will be getting around 0.39 of n naught. That of course you can write as 0.39% of the original amount. So this is nothing other than 0.39%. So that is what has been given over there. So you can say even the fourth option also is going to be true. So first option is correct, second is correct, third is correct, and fourth is correct. Then what is the right option for us? It is A, B, C and D. All the 4 options are true in this particular problem number 11. But one thing, okay, this type of a problem, if it appears in the exam, it is simple and easy. But it takes a little more time for us to solve, because all the 4 we have to check. Whether all the 4 are correct, or 3 are correct, or 2 are correct, or 1 is correct, like we have to decide. So it takes a little more time for us. That is problem number 11 in this particular order like. Next, number 12 is given this way: the fraction of a radioactive sample that will decay during half of half-life period. In fact, we all know in one half-life period it becomes 1 by 2, half of the original amount. Half of that half-life, it should now become 1/4. What is the fraction of radioactive sample that will decay? That's what he is talking. During half of half-life period. We know n by n naught is equal to 1 by 2 to the power small t by capital T. That is the usual formula. Now here he has given you small t is half of the half-life period. So if t is half-life period, I now can write this one t by 2 divided by t. So I think all of you might have understood t must be half of the half-life. So what will this value now be? 1 by 2 to the power half. So every one of you can understand it is now 1 over root 2. What is this 1 over root 2? It is the amount that is left there, undecayed. Undecayed part is that much. But he is not asking you undecayed part there. He is asking you to calculate the fraction of the amount which has been decayed there. So what we can write now? The amount, right, that is decayed. I just want, what is that value? 1 minus 1 by root 2. So it now becomes root 2 minus 1 by root 2. So check those options once again. First option is given 1 by root 2. Second option is given 1 by root 2 minus 1. And third option is given root 2 minus 1 by root 2. And fourth option is given 1 by 2. So what can we write now? The correct answer for this particular problem is C. That is the third option for us. Once again, just understand this part. N by N naught is 1 by 2 to the power small t by capital T is known to us. Small t is the total time taken. Capital T is half-life period. Now total time taken is half of the half-life. That is what has been mentioned there in the problem. So half of capital T by capital T. When I write like this, that becomes 1 by root 2. That is the amount decayed remaining. Now we want amount decayed. What is this value of amount decayed over here? That amount decayed is nothing other than 1 minus 1 by root 2, which now becomes root 2 minus 1 by root 2 as such. The correct answer is going to be third one, that is C for us for this problem number 12. Check the problem number 13 now. The carbon 14 to carbon 12 ratio in a certain piece of wood is 25% of that in atmosphere. The half-life period of carbon 14 is 5580 years. The age of wooden piece is how much? In fact, 4 options are given this way: 5580 years. Second option 2790 years. Third option 1395 years. And fourth option 11160 years. Probably all of you must have got this idea. Radiocarbon dating we used to take up. Carbon dating is the methodology by means of which we people used to estimate the age of fossils, age of wooden pieces, or age of rocks, and so on and so forth like. This actually is one of the important most methods what we people used to adopt to estimate the age of a fossil like. Now in this particular case, carbon 14 to carbon 12 ratio in a certain piece of wood is 25% of that in the atmosphere. 25% only it has got now. You can certainly understand 25% is nothing other than 1/4. So what is that 1/4 here once again? N by N naught must be equal to 1 by 4, which now is 1 by 2 whole square. But according to the formula, it is 1 by 2 to the power n we people is to write. This is the original formula we know. If you just equate these two, you come to know that n is equal to 2. What is this n over here? N is nothing other than number of half-lives. So what is the half-life period given? It's 5580 years. Therefore, age of wood is asking you. What is this age of wood now? 2 half-lives. So 2 times the half-life period. What is the half-life period given? 5580. If you just multiply these two, 11,160 years you are going to get. So what is the age of that wood now? 11,160 years. Followed. So this particular process is adopted to know the age of wood like, or the age of trees like, or the age of fossils, rocks, and so on and so forth. It's called carbon dating. That is actually the concept what we have to understand. So what is the correct option here? The correct answer for this one according to the given options is now D. That is the important feature of it. So one of the excellent model questions, once again, that method is important, that is called carbon dating. Remember that. Check the next number, that's 14. The half-life period of a radioactive element X is the same as the mean lifetime of another radioactive element Y. Half-life period of X is equal to mean lifetime of Y. In reality, all of you know pretty well, half-life period by formula is 693.693 by lambda. This of X I am talking, and it is equal to mean life of Y. Mean life is taken as 1 by lambda, that of Y. That is what he is asking you. Let us continue the remaining problem. Initially, they have the same number of atoms. Initially, they have the same number of atoms. Then, he has given you 4 options. X will decay faster than Y. Y will decay faster than X, the second option. X and Y have same decay rate initially, that is the third option. And the fourth option is given this way, X and Y decay at same rate always. Not only initially, like always they are going to have the same rate of decay, that is same rate of disintegration. That's what has been mentioned there. What is the correct option out of these 4? And this question has been asked way back in 2007 in the JEE paper. Purely theoretical, there is nothing in that. The way he has given you 1 by lambda of Y is equal to 0.693 by lambda of X. So certainly you can understand lambda of X in this particular case is going to be 0.693 times the lambda of Y. So certainly you can understand when lambda of course is more, then you can definitely understand its half-life span is going to be less. But in this particular case, for X you will be finding the lambda value as less. That in the sense, the value of half-life period is going to be less. That means what you can understand, it disintegrates faster than Y. So what we can understand from this particular relation, you can certainly understand X decays faster than Y. Just observe this result, nothing else. So X decays faster than Y. When X is decaying faster means it is understood its half-life span is supposed to be as small as possible, as less as possible. Then the decay is going to be more. So if you take up this one, this X decays faster than Y is tallied with the very first option for us, that is A in this problem. So just understand what is of X equal to the value of Y. Average life of Y is equal to half-life of X. That is numerical relation he has just mentioned. So identify from this equation that X decays faster than Y. So that is the correct option, that option is A for problem number 14 what we have. In 2003 JEE paper, a very peculiar question has been asked. purely on basics, nothing else. That question is this problem number 15. Let me read it out first. A nucleus with atomic number 92. Z value has been mentioned here, that as 92, emits the following in a sequence. What it is emitting, he has given a long chain there. What is that chain? Let me read out. It is emitting the following in a sequence. That's the concept. First alpha, then beta, then 4 alphas in a row, then 2 betas in a row, then again an alpha, then 2 beta plus particles, then one more alpha. A long chain he has given, as I said. Let me write that chain over here. He is just giving first alpha, then beta, then again beta. Order. The same sequence he is talking about. Then it has emitted alpha, 4 alphas in a row. Then again he has given you 2 more betas, beta minus, that is beta, then again beta. The disintegration has not been over yet. Then he said one more alpha. Then this time he has given you 2 beta plus particles. Then again one more alpha. This is the total sequence what has been mentioned. Just look at the order. Alpha, then beta, then 4 alpha particles in a row, then 2 beta particles, then again an alpha particle, then 2 beta positive particles and one more alpha. Total, this is the chain in the same sequence. That particular nucleus is now emitting. He has given that has been emitted all this. Now the question is the Z value, that is atomic number Z of the resulting nucleus is how much? And he has given you 4 options. One is 76, the second option is 78, third option is 82, and fourth option is 74. First and foremost, try to just recollect once again. Whenever an alpha particle has been released, if an element Z, XA, gives out an alpha particle, you get Y, which of course will have atomic number reduced by 2 units and mass number reduces by 4 units. So whenever alpha particle has been released, atomic number goes down or decreased by 2 units and mass decreases by 4 units. Similarly, if X, which is ZA, is giving out one beta particle by any chance. Beta particle is a fast moving electron. We all know that one very well. And what is that beta plus particle here? That is now to be called positron. Electron and positron, these two are antiparticles of one another. So when beta particle is a fast moving electron, beta plus particle we can take it as fast moving positron. That is the concept. So if you look at here one beta particle, if it is given out, then naturally you get once again Y like. You will never have any change as far as the mass number that is concerned. Mass number remains here only. Whereas atomic number increases by 1 unit. In fact, these 2 points you people have to recollect before taking up this problem. But one thing you can understand, this positron, this electron, the result will be the same in both equal and opposite. So you can cancel them off. So how many total number of alpha particles we people are getting out of that nucleus? 1, 2, 3, 4, 5, 6, 7 and 8. Totally 8 alpha particles. And how many beta? 2 beta particles. So ultimately 8 alpha and 2 beta are released from that nucleus what is given in the problem. So his concentration is only on atomic number, not on mass. He is not asking you what is the mass number of that element. He is asking you only atomic number of the element. Therefore, 8 alpha particles means 8 into 2. 16 will be reduced over there due to alpha particles. And what about beta? When it is releasing a beta particle, atomic number will be increased by 1 unit. Now here, this much it is losing, and 2 beta particles means 2 units will be increased there. So what we should write now? Z present value of Z is equal to 92 minus 8 into 2 and plus 2 into 1. Why this 2 into 1? You can understand 2 beta particles when they are being released from that particular nucleus, its atomic number increases by 1 plus 1, 2 units total. So this now is going to be 92 minus, this is 16, minus 16 plus 2, it's minus 14. So exactly you will be getting here 78. So 8 into 2 it is going to be lost due to alpha particles. 2 into 1 it's going to gain due to beta particles. So that is the identification you need to have. So if you look at here, out of 92, 2 into 8, 16 will be lost due to the emission of alpha. After that, 2 into 1, that of course is gained due to the emission of 2 beta particles as such. So totally what will now be its present atomic number? That is 78 for us. Seeing the options, 76 the first option, 78 the second option, 82 the third option and 74 the fourth option. So what is the correct option here? You certainly can say the correct answer for this one is the second option, which is 78, that is B in this particular problem. So problem number 15 has got an option 78, that is B, the correct answer. All of you should just focus on this part of it. Once again I repeat, whenever a nucleus gives out or releases an alpha particle, its atomic number will be reduced by 2 units and mass number will be reduced by 4 units. Similarly, if it gives out one beta particle, its atomic number will be increased by 1 unit, whereas its mass number will not be affected by this type of an emission. So these areas we have to concentrate on to solve this type of a problem, which has in fact been given in 2003 IEEE paper for us. So that is the importance of this problem.